Topic for today is wave interactions. So we've got 4 different types of wave interactions that we're going to be discussing today. The first 3 of them are all ways in which waves change their direction or interact with a boundary or a new medium. The last one is going to be what waves do when they meet other new waves. So to start, our first one that we're going to go through is one you guys interact with pretty regularly, reflection. And reflection occurs when a wave bounces off of a boundary. Occurs when a wave bounces off a boundary. Okay. Now, the easy example of this is, of course, what? Your reflection, a mirror, absolutely. Mirrors. What else is a reflection, though? What else is a reflection or uses reflection? Say again? What do you mean by water? Okay, so your reflection in water, so light reflecting off water. Off water. What else is a reflection of a wave? Any other ideas? Come back to that one later. Nope, shadow is not a reflection. What about things that are reflected that aren't light? Matt, you've got an idea? Okay. What about reflections that aren't light? A ball? I'm not saying you're wrong. I'm just saying I don't understand what you're saying. Okay, I get what you're saying now. Because it's not traditionally what we would call a wave, I'm going to go with no in this case. What we're going to mention in a minute, the law of reflection, does work for it because it does still bounce off following the same rule. But because it's not a wave, I'm not going to throw that one in here. Can you think of an example of what a sound wave reflecting would be? Echoes, absolutely. All right. How about a sound wave reflecting off of a moving object? Anything that would use that specifically? Anybody think of a technology that we use that works with bouncing sound waves off other objects? Or that animals use where they bounce sound waves? Okay, so we can go from echoes. We can also talk echolocation. Anybody know what that is called when we use it underwater? Sonar. Okay, we could also say radar. Sonar. So you've seen the movies where there's a submarine and you hear beep, beep, beep as the little things going around the green screen and scanning where the other things are underwater. If not, you need to see some submarine movies. Say again? They might do that in Aliens. That's probably radar, though. Okay. All right. So, aside from light waves and sound waves, we could also see this in water waves. If you're in a pool and a wave reaches the end of the pool, it bounces off the pool wall and comes back out towards the water. So we could say water against the side of a pool. Same thing, yep. All right. So regardless of whether we're talking about water or light or sound, all of these different types of reflections obey what we call is the law of reflection. Law of reflection. And the law of reflection states that the angle created between an incident wave and the normal is always equal to the angle created between the outgoing or reflected wave and the normal. So the angle created between an incident wave and the normal is the same as the angle between the reflected wave and the normal. The reflected wave and the normal. All right, where have we heard normal in physical science before? Yeah, absolutely. Normal force. What was a normal force? What was a normal force? Say again? You keep having ideas, you just don't want to tell me them. All right, somebody else got an idea then. What is a normal force? When did they act? What was their purpose? The ground was an example of a normal force. What else was? Or what other examples did we use? The table. So when you set something on the table or when something stood on the ground, the normal force was the ground or the table pushing back up on them. And the reason we use the same word, normal, in this case, is because normal implies that it's perpendicular to the surface. So when we talked about a normal force, if the surface of the table was flat, then normal force was straight up. In this case, if we're talking about a normal of a mirror, then that's a line that's perpendicular to a mirror. So if this is my mirror, this would be the normal. And if we want to show the law of reflection, then we take a wave that's incoming and show that it creates an angle with the normal. And I'm going to call that theta I. Theta is a Greek letter. It looks a lot like O with a hat. And I'm going to say this is the angle of incidence. And the outgoing wave here creates an angle with the normal, theta R, and that's the angle of reflection. Brooklyn, you had a question? Okay. So, relating the angle of incidence and the angle of reflection. This is probably the most complex equation that we work with all year. So make sure you're paying close attention to this one and you're following along. Okay, so theta I, this would be our angle of incidence. The angle created between the incoming ray and the normal is equal to theta R, which is the angle of reflection, the angle created between the normal and the outgoing wave. Good? Should I go back over it? Okay. So, waves coming in here. We could say that, like, in this case, let's, I'm going to draw it over here with a little fewer words. There's my normal. Here's a person staring at themselves in the mirror in the morning, and evidently they're a giraffe. So they have light rays coming from, oh, I don't know, their shoes. They're looking at their shoes in a body-length mirror. I know some of you do it. Don't lie to me. All right, they look at their shoes in the body-length mirror. This creates an angle, theta I, between the normal and the light coming from their shoes. They're looking at their shoes, so the light's coming to their eyes. This angle between the normal, again, a perpendicular line, and their eyes is the reflected angle. And these two angles have to be the same. So when you're driving in your car, anytime you look in a mirror, the angle created between what you're seeing in the mirror and the mirror's surface itself and your eyes in the mirror is always exactly the same. All right, go to this incredibly complex equation relating these two variables. It's always the angle of reflection because the reflected light's coming to your eyes. Okay, so you're saying, like, what if I've got the sun here and a mirror here and some bright spot there? then the light coming here, coming there, bounces there, and this is my normal. This angle and this angle must be the same. Good? All right. Questions on reflection. Then we move to our next topic, which is refraction. All right. Refraction. This is when a wave bends due to changing a medium in which the new medium has a different wave speed than the old one. This is when a wave bends due to a change in medium in which the new medium has a different wave speed. Has a different wave speed. Do you guys remember the fish tank that I had up here like a month and a half ago? And some people came up and they saw that if you look through the fish tank, the water distorted where things looked like they were. That's refraction. Okay. Alternatively, if you think about looking into the water from above, say you're at a lake or a river, and you see a fish in the water, is the fish where it looks like it appears to be? No. People who have tried to either spear or bow fishing or who have tried to just net the fish know that it's not where it looks like it is, because as you look into, or as the light comes out of the water, the light bends. It refracts as it's passing from a medium with one speed for a wave into a speed or new medium with a different wave speed. So aside from things like spear fishing or bow fishing, what's another example of a light wave or a wave of any sort changing its path because it's entering a new medium? It's another example of light bending or a wave bending because it enters a new medium. No, shadows really are just the blocking of light. I mean, we could argue that they're the next topic, but not this one. So what other examples could we have of a wave bending? Your explanation's wrong, but your example's right. So a rainbow is a good example. So a rainbow is a good example because as light is passing through the water droplets in the air, water droplets have a different wave speed than the rest of the air does, so the light at different points refracts or bends its path. And we actually get the different colors for a rainbow because the amount of bending each different color has is slightly different. Right? Other examples. I can see that at least 1, 2, 3, 4, 5 different people in here. Say again? Glasses and contacts. Without your glasses or contacts, light would be traveling in a straight path, which for those of you who need these, then you really can't see things well. However, as light passes through your glasses or contacts, it refracts, meaning it starts on a new path, and it's redirected towards the back of your eye where it can better form an appropriate image. Okay? So glasses and contacts work here. Now that we've got those on our list, any others that you can think of? Windows can. We try to avoid having them do that because it distorts what you see. But I'll put Windows on this list because it can happen. It shouldn't if it's a good window. Anybody else? Yeah. What do you mean? I'm not going to say no because there could be an example here. I'd need to know more about what you're thinking to really give you a yes or a no there. So I'm going to go with maybe until we've got clarity on that one. Okay? Other examples that could be refraction. Absolutely. Magnifying glass. or a microscope? Anybody else? I'm going to put things like a hunting scope on here, and we'll call that good for now. All right, so after refraction, the next one we've got is what we call diffraction. Diffraction is the bending of a wave as it passes an edge. The bending of a wave as it passes an edge. Has anyone here been to a harbor or bay where they store a lot of boats? Typically on like the ocean. Okay, yes. How do they protect those boats from ocean waves? Okay, docks are one thing, but they could then crash up against the docks pretty well. Say again? All right, so the buoys that help cushion you against the docks. Right. Yeah, absolutely. So when you work with bays and harbors for the ocean, one of the things that they create is a wave break. So if out in the ocean we've got all these waves, and these waves would rock the boats and crash them against docks and such. One of the things we do to make the bay more calm is we create a wave break. So a wave break is typically either an earth and rock or maybe a concrete barrier that the waves can crash upon and then they stop. However, we leave a gap in that for boats to come in and out of. Now, because boats can come in and out of that, well, so can waves. Now, if waves didn't diffract, we would see waves come through in a very straight path. And we'd have like a laser beam of waves that would strike specific things in a straight line. That's not what we see. That's not what happens when waves pass through a wave break. Instead, they start out narrow, but they get wider and wider as they travel forward. The reason for this is that waves, when they pass an edge, bend. So the waves coming here start to bow out and around. And these waves, while they're spreading out, they're getting weaker, but they are covering more and more territory. So the whole bay does get some amount of small waves, but they're much weaker and they're of lower intensity as a whole, and we don't see as much disturbance inside the bay. Now, you can also notice this happening right now inside the classroom. Where? What do you mean? Okay. So if you take a look underneath the cabinets, where are the undersides of the cabinets getting light from? The lights, right? Well, if you were to draw a straight line from the lights to the underside of the cabinet, what's kind of in the way? Cabinets. So as the light's traveling to the cabinet edge, when it gets to the edge of the cabinet, the light actually bends around the cabinet edge, which is why we can see everything here. If light didn't diffract, this would be pitch black. We wouldn't be able to see anything here. It'd be dark as night. And because it's not dark as night right under here, that means that the light has to bend as it comes around the edge, so that it actually illuminates those other spots. So for those of you who are saying a shadow earlier for the other examples, I said to hold on to that idea for this one. Well, when you look at something's shadow, is it pitch black and you can't see anything there? No. That's because light is diffracting around you, bending around you, so that it can partly illuminate that those spots behind you. So we could have examples like wave breaks, shadows, or let's say you have a door that's slightly ajar and you hear someone talking out in the hallway. Well, their sound can be partly diffracting through the doorway, which makes it into you so you're able to hear it. So sound around doorways. All right. Questions at this point about refraction, reflection, or diffraction? Ooh, I did forget one example that I want you guys up on refraction, this one here. Talking about waves as we enter new materials. So ways in which refraction can be used is for identification of things like gemstones. Eighth grade, you probably learned a way to identify diamond from glass for jewelry. How would you have learned, what would you do in earth science as to tell a diamond from glass? Anybody remember? Say again? You telling me that you guys never learned the hardness scale? Well, eighth grade teacher should have talked to you about the fact that different materials have different hardness. Diamond, yeah, there we go. So I did say something to you. Good. So if you want to know what your eighth grade teacher should have taught you, yes, the streak thing, where different materials have different hardnesses and can't be scratched by things that are less hard than them. The diamond being a 10 on the scale and being impossible to scratch or cut a diamond with a diamond. Sound okay? Good. If we wanted to test these things without a hardness test, we could actually use refraction in order to test it. If we had a material that was supposed to be a diamond and light into it, as light passes into the diamond, it bends its path. As it then passes out of the diamond, it bends again. By determining what the path is between here and comparing them and saying, well, this is how much it would bend if it's diamond, and this is how much it would bend if it were glass, we can determine what the material actually is using a laser. So we can shine light through a diamond or something that's supposed to be a diamond, and depending on how much that light bends, we can tell whether it's a real diamond or if it's a fake without having to scratch it. All right. Questions about that idea for refraction? Okay. And the last idea. So we've talked about three different things so far. We talked about reflection, refraction, diffraction. All are ways you can bend a wave. Now we're going to talk about what happens when two waves meet each other. So this is wave interference. Okay. So to demonstrate wave interference, I need everybody at one of these tables to take your table and slide it to the side. Meet the amplitudes add to a greater value. A greater value. And this is called constructive interference. And the opposite, when a crest and a trough meet from two different waves, they cancel each other out to make a weaker amplitude. Crest and a trough meet. The amplitudes subtract. To a weaker value, to a lesser value. And this is known as destructive interference. This that we're talking, of course, is standing waves. Note, standing waves. And a standing wave is created when a wave reflects back on itself. When a wave reflects back on itself. Okay? When this happens, it creates alternating zones of constructive and destructive interference. Zones of constructive and destructive interference. Go ahead.
So how do you remember all these definitions word for word? How do you remember all of them?
Because I've been doing this for 8 years. Wow, ouch. I don't know. I mean, my first couple of years, I had to look them up over and over. Now I just, yeah. Yeah. And of course, the definition is something that I'm not as worried about having exactly word for word like what's in the book, but I want the main ideas there. So in the same way, if I asked you guys to define some non-science term, like, I don't know, station, you guys could give me several different definitions for the word station, right? I don't know. It was the first word that came to mind. Don't ask. I have no idea. But you could tell me different definitions for it, and not all of your definitions would be the exact same, but they would mostly all be right? So the definition I'm giving you is right, but not necessarily like exact word for word out of the dictionary. All right, so we've got, that is the definition for standing waves. Nodes are locations of completely destructive interference. Locations of completely destructive interference. And antinodes, which are those big lobes that you can see that vary between constructive and destructive. Antinodes vary between constructive and destructive. All right, so we've talked about waves with examples that had to do with light, especially when we talked refraction and reflection. We talked about waves that had examples to do with sound, such as, again, echoes. We talked about waves that had to do with water. We saw that for diffraction. We've also now done examples with things like rope and slinkies. Now, waves don't have to be created in these nice fluid substances, things that can move easily. Waves can be created in things that really shouldn't move, or things that are supposed to be constructed very firmly, like, let's say, bridges,